So now abstract, so I will come to this definition. So abstract algebraic set or algebraic variety. Okay. So see, so it is a triple. So an abstract algebraic set is a triple. X. So I write this has nothing to do with anything, okay, before regular functions or anything. So what is it? I will define. X is a set, Kx is a finite type reduced K algebra, and phi is a bijection between the maximal ideal of Kx and X. So, it is a set theoretic bijection. So, Kx you do not think as this is a regular, I am not assuming X is embedded in somewhere, X is just a set.
Kx, apart from being a finite type reduced K algebra, you do not have any
connection with that, but only the connection with X is this phi. You take the maximal ideals of Kx, you have a, just see Hilbert-Null's search. If you started with X is in Kn, An, consider the coordinate ring, go Kx1, x2, xn modulo Ix, you have this natural. So now I am saying, so you have this triple. Now I am abstractly I am defining, because I do not want my An. I somehow want to get rid of this An. So I want to define it like this. It is a set, a finitely generated K algebra and a bijection with the maximal ideal of K algebra with maximal ideals of the K algebra with the set X. Is it clear? So the element of Kx.
With this definition of algebraic variety, if you go back to the usual algebraic set definition,
Yes.
you coincide with that.
Yes.
For example, here the singletons are associated to maximal ideal.
Yes.
So if we are taking an algebraic set there, it will associate to a radical ideal. So
Yes.
if we are taking the algebraic set in X,
Yes.
will it get associated to the radical ideal through this bijection, or we are looking for some specific bijection?
Now bijection is also important. Yeah, bijection is important. P. But often we will omit that. We will write for every point of X a maximal ideal. Which so what we will write that for every point of X I have some association. So whenever I have a algebraic variety or abstract algebraic variety, I associate every point of X with a maximal ideal Mx in Kx. This is a maximal ideal. This association is important. We will see in isomorphism when Kx and Ky are isomorphic, then this Mx should go to My. See, how do you say two objects are same? You do not have any same thing. It has to be isomorphic. There is some two rings are same, does not make sense. Same makes sense if it is a subset of something. If it is not a subset, see, this way we are trying to do it embedding free, right? So there is no subset. So up to isomorphism, everything is up to isomorphism. So the elements of X are called points of the variety or close points of the variety. since we are doing variety here, everything is a close point. So, we will not worry about all this scheme structure and all. So, and the elements of the algebra Kx are called functions on X. Or regular function are called are regular. In fact, you can see it very naturally. So, naturally you can see these elements of Kx, they are functions, you can think as a functions on X. How? So, see Kx is a finitely generated algebra, right. So, now Kx to Kx modulo phi x, there is a map. Phi x is an ideal, maximal ideal, alright. So, now it is Hilbert-Nullstellen's, there is a first of all there is a isomorphism between Kx modulo, because it is a finitely generated K algebra, assume K is algebraically closed. So, you have some isomorphism, and this isomorphism is canonical isomorphism. After all, K is there is a map from K to Kx and Kx to Kx modulo Mx. So, this map is also, this is called structure map. So, we call it beta. Huh? Oh, sorry. So, phi is here. So, if I call it this phi inverse, if I call this phi inverse, then phi is a map from X to spec the maximal ideal. Huh? So, now I have a map. So, if I take any element here AF, and this is a canonical map, because phi x after all is a maximal ideal. So, Kx to Kx modulo phi x, this is a canonical map, and there is a structure map which is beta. Take beta inverse. So, if I compose beta inverse composition pi, then I get a map from Kx to K. So, then you define beta composition pi of f as f of x. This is pi x because it depends on x. So, it is naturally, I mean, you can think as these are functions, f as a function on x, right. Sorry, I am writing something different. I think I should write first pi x, yes, first pi x, and then apply beta inverse. That's what I wrote before. This should be. So, now as I said that now often see I will not write this phi. Huh? F of x should be a function in f element of k, right? Yes. Oh, sorry, beta I was writing as in this direction. Okay, so if I write this beta in this way, so then no, sorry. See, structure map, I was talking about structure map, right? Structure map is from K to Kx mod phi x. Kx is a K algebra. So, there is a map from K to K is sitting inside Kx. That is the structure map. And then you are going from Kx modulo phi x. So, if there is a map is from K to Kx mod phi x. So, that is why beta is in this direction. So, you take the beta in. And this is a canonical map. There is no choice here. Yeah, Kx, yes. So, that is why I wrote beta inverse. So, you can think this element in abstractly also, this element of this finitely generated K algebra as functions on x. right? You can evaluate at the point. Whenever you think as a function, f is a function on x means at every point of x you can evaluate, there is some, you can make sense of that. So, this is the abstract way of making sense of that. Okay. So, for simplicity, of notation, we write x k x instead of x k x y. So, abstract algebraic variety is this pair of set x and a finitely generated algebra kx. So, giving a algebraic structure on x. So, if I have a set, giving a algebraic structure means I give a finitely generated k algebra kx such that it has a bijection with the maximal ideal of that with the underlying set. Okay. So, now once you define some object, you have to define what is the morphism between this. So, morphism between two abstract varieties. Algebraic sets of variety. So, suppose x, kx, there are two such objects. So, this consists of two things. One is a map f which goes from x to y, and another one is f hash, where f is a set map from x to y, and a k and f hash is a k algebra map from ky to kx, such that there should be some relation between f and f hash, right? It is a two set map. One is algebra map, one is a set map, but there should be some relation between f and f hash, and that is what this f hash of g at x should be g of f of x. So, f hash of g you think as a function on x, you can think as a function on x. So, f hash at g at x you can evaluate the way I define. What is the evaluation of a element of ky on a element of y? So, sorry, or element on x. F hash of g, it should be element of k in this ring, and if you evaluate at x by this canonical way, that should be g of f of x. So, this is the evaluation of g at fx. This has k algebra homomorphism. Sorry, thank you. Not x is reduced, kx is reduced, kx is reduced, yes. See, if you don't have reduced structure, you will see them that you start differentiating between f square and f cube. But for example, if you take this ideal kx modulo x, and kx modulo x square. As maximal ideal there is one point, but this has more functions. This as a ring, these two are not isomorphic. Or as regular functions, if you think this is a regular function of some algebraic set, this has a regular function of some algebraic set, they should be different, right? But if you take the maximal ideal here, this is only one point, and here also it is one point. So that is because here you have some nilpotent, so there is something wrong, because you want, because now they both has only one point, so they should be isomorphic, but the ring of regular function, which is kx modulo x square, this is called this has some name anyway. So this is this is not. So if you have regular function which is nilpotent, which is very strange in geometry, that we have objects where we have nilpotent elements. Nilpotent does not mean the element is 0. In rings, whenever you have a commutative ring, the nil radical, if it is not 0, that means you have element which has a 0, which is not 0, but some power is 0. So if such ring appears, then you are in trouble in doing this theory. So that's why you need, this is one of the reasons why one needs to do scheme theory, where maximal ideals are not only the thing, you have to consider prime ideals. So this was the idea of Grothendieck, that he said that if for every commutative ring there should be some geometric object. So commutative ring also has some nilpotent elements. So reducedness will play a role when you have this this is called thickening. This point, there are more functions, there is only one point, but there are more functions. It's like a cloud around that, but only one closed point, but so when you study scheme theory, this will appear again and again. So that is one concept, one motivation to study. If you drop the reducedness, if you drop the finiteness, then you are in trouble. Then you solve non-Noetherian scheme and all things will come up, and that's also, some people study that, but one can drop this reducedness condition and study scheme theory. That's one motivation to go into a larger category where you allow reduced, non-reduced regular function. So this is now. So, but you see that, yeah, this is a digression. Now you see in this definition, this f and f hash, sorry, this is f hash. This f and f hash are interrelated. They are not very different from each other, because when you define f hash, you are using f, or when you are defining af, you are using f hash. Huh? Which one? Yeah. Yes. Set map. Set map. This is a set map. I define a abstract algebraic variety as set and a finitely generated K algebra and some bijection with the maximal ideals with X. Right. Now you see that I am very close to the coordinate free approach. Now I say it is isomorphism if this is isomorphism. If there is a bijection between x and y, and if this ky to kx is a isomorphism which satisfies this. That is my isomorphism of abstract algebraic variety. Now it is embedding free. That is what is a nice, I mean, that is what the point. I mean, you should not bother about where it is embedded. When you define some object, you should define it like that. So this is a more natural way of defining affine varieties or algebraic varieties, or this is to have a embedding free approach. Okay. So I will stop here. So we will continue tomorrow with examples. We will see some examples where this different embedding, but they are same as have isomorphism. Yeah. I will stop here.